So we're about to do one of my most favorite parts of all of chemistry. This is sections 7.3 and 7.4, the hydrogen atom and the Bohr model. And I always get goose pimples when I do this particular one, but I don't know how it'll be when I'm doing it on video, because you guys aren't here to see me. I can't see your faces, as if you really get this whole concept, it's just so utterly cool. So let's start. There's this idea that electrons can only exist at discrete, not continuous, amounts of energy in a hydrogen atom. And we've talked about continuous spectra in prior chemistry classes. In a continuous spectrum, you see all the colors of the rainbow. When you see a rainbow in the sky, that's a continuous spectrum. The light from the sun is getting scattered by the raindrops, creating all the colors of the rainbow. So there's evidence that hydrogen and different elements, all elements, do not have this continuous spectrum. They have a discrete spectrum. And the evidence is that we can excite hydrogen atoms, and we'll look at this in class. We excite hydrogen atoms with energy. This causes hydrogen to emit light, and we can see the light that it's emitting. We separate the light that's being given off with diffraction grating, and we get discrete lines for the spectrum representing discrete wavelengths. So over on the left side here, we see this is an example of the hydrogen spectrum. These levels here, the 5, 4, 3, 2, those are the shell numbers N. Maybe you remember N is the shell number from last year. And we get a red, a green, and a blue color. There's also a violet, high purple color that's very hard to see that isn't being shown in this particular graph. And this is for electrons jumping from any shell down to shell number 2. Right here, this would be shell 2. And the idea is we get specific colors depending on whether we're jumping from a higher shell number or a lower shell number. All right. And what's the idea here? Let's look at this picture. Okay. The idea is we add all this energy to electrons. They get excited in the hydrogen atom. So the electrons get excited, they get all this energy into them, and the electrons will jump from any shell. Usually they'll start off at, not usually, if they're at the ground state, they're starting at shell 1. The electrons will jump to a higher shell number because they've been added energy. So we add energy E. And now that atom would be unstable. The electron can't stay out at shell, let's say I drew it out to shell 4. Can't stay there. So the electrons would jump back down to lower energy levels, giving off the difference in energy, delta E, that's a difference in energy. Gives off the difference in energy as a photon. So over here we're showing that an electron is going from shell 5 down to shell 2, and it's giving off this wavelength of blue light. And when we look at the line spectrum, we'll see this blue line, which is showing up as red. Let's make that blue. We'll see a blue line in the line spectrum. And if electron jumps from shell 4 down to shell 2, we get a wavelength, a photon of light, that gives this green light. And if we jump from shell 3 down to shell 2, we give off a photon of light. Remember, these photons can be particles or waves. And that would be the red line that we see in the line spectrum. Now here I've given you, over on the left side, I've given you the actual lengths of these particular lines, and you can measure these when you're looking through diffraction grating. And there is an equation. It's called the Rydberg Equation. This number right here, this 2.178 times 10 to the negative 18 is called Rydberg's constant. And we have all this evidence that says that the energy of an electron in shell N is the shell number, for the electron. The energy of the electron in shell n is equal to negative 2.178 times 10 to the negative 18 joules times 1 over n squared, where n, again, is the shell number of the electron. Okay, so the delta E, the change in energy to go from one shell to another shell, would be the energy from the shell you started at, energy at the shell you started at, down to the energy, or minus the energy at the shell where you end up. So it would be energy at the final position minus the energy at the initial. And I actually showed that to you backwards. So it would be, if we're going from 5 to 2, it would be final minus initial, because remember, delta is final minus initial. So it would be the energy of shell 2 minus the energy of shell 5. And we're going to go through and actually do that calculation. We're going to find something that's so cool. So here's the kicker. The line spectrum that we see is for electrons going from any shell n down to shell 2, not including shell 1, because we have to go down from somewhere down to shell 2. So in fact, these wavelengths that we have here, that I've shown in this box, are actually for going from shell 5 to 2, from shell 4 to 2, and from shell 3 to 2. And I mentioned that before. I keep saying that again. I showed that wrong on that last one. Hold on a second. Shell 3 to 2 would just be the little one right there. Okay, and these wavelengths, you can actually get them out of these equations that we have, and they are, when we measure them, those are the actual wavelengths that we get. So let's look at our equation. We can calculate the change in energy, the delta E. Once we calculate the delta E for going from one shell down to shell 2, we can calculate lambda, and we get these wavelengths out of that for each shell, 5 to 2, 4 to 2, to 3 to 2. I just find this amazing, because we just have this simple little equation, and this 1 over n squared, n is your shell number. Those are whole numbers. It's just 5, 4, 3, 2, 1. Just, you know, it's just a shell number. And that equation holds. This equation holds. So let's actually do, I don't know if you're getting this yet, how cool this is, but let's do an actual calculation. We're going to calculate the change in energy to go from shell 5 down to shell 2. So that would be, this is the energy for shell 5. Nope, final minus initial. So the first one would be the energy for shell 2, E2, minus, this would be the energy for shell 5, E2 minus E5. And E2 is just Rydberg's constant, 1 over 2 squared. E5 is Rydberg's constant, and 5 squared. We calculate that out, and we get a number, whatever, no big deal. We just get this number, negative 4.574 times 10 to the negative 19 joules. Doesn't seem very important right now, no big deal. By the way, this is negative because energy is being given off when you go from shell 5 down to shell 2. So the difference in energy is negative. That just means it's an exothermic system. That's an exothermic change, energy being given off. Now, we have our equations, E equals h nu and lambda nu equals c. E equals h c over lambda is what we got from before. Now let's cover this up. So we have E equals hc over lambda. That's the equation we get when we combine E equals h nu with lambda nu equals c. We have our energy. We know h. We know c. We can solve for lambda. So that's what we're doing right over here. Just plugging in the energy that we got right here. Now you'll notice I got rid of the negative sign. That negative sign we don't put here because we're getting a wavelength, and the negative sign just represented whether energy was being given off or taken in. And we know energy was being given off, so there should be a negative sign for the energy. But now when we calculate lambda, we take the absolute value of the energy. And Okay, so we get a number 4.35 times 10 to the minus 7 meters. Now remember, we talk about light in terms of nanometers, the wavelengths of the visible range of light, nanometers. So we'll convert that. We get 435 nanometers. That's the blue line in hydrogen spectrum. Okay, cool. A. So what we had up here, let's look back up here. From shell 5 down to shell 2, I don't know what just happened there. Let's get rid of that. From shell 5 down to shell 2, we found an energy. We calculated the energy right here. Plug that into E equals hc over lambda. We found that we calculate this wavelength 435 nanometers. Now experimentally, if we look at the hydrogen spectrum, we get a wavelength of 434 nanometers. And within sig figs, 434 and 435 are the same number. If we did this same calculation going from shell 4 down to shell 2, same exact calculation we just did, we would find this 486 nanometers would fall out of that equation. And from 3 down to 2, we would get the 650 nanometer line. That we physically see this. This is what we see right here. When we excite hydrogen, we look at it through diffraction grating, we see these 3 lines. They correspond to these wavelengths. Those wavelengths correspond to these delta E's for shells 5 to 2, 4 to 2, and 3 to 2. And to me, that is one of the most amazing things in life. Okay.